Hello, and welcome to the Characteristics of the Sample Mean lecture. So just a warning, this lecture is going to be pretty heavy in some statistical theory. So if you need to watch this more than once or go through the PowerPoints more than once, that's totally understandable. I'd encourage you to do that, as well as if you need to take notes. You guys should be taking notes, so please be doing that. But with that being said, let's get cracking on characteristics of the sample mean. So first, before we start, knowing the difference between a population and a sample is important. Now, keep in mind that your population is defined typically. You state, oh, we're interested in the test scores for the 40 students in the class. That is the population. It just says we're interested in the test scores for the 40 students in the class. We're not saying anything else. We just care about those 40 people. That would be our population. It doesn't say anything about generalizing that group of 40 to the wider realm of people. It's just, I want to know about the test scores and the 40 students in this class. Population. Now, we are interested in the test scores for all introductory stat students. We obtained the test scores from 40 students in Professor Cooper's class. That's a sample. It's that first part that's imperative. That is defining our population. We're interested in the test scores for all introductory statistics students. Excuse me. Well, obviously, there's more than 40. So to say that, oh, we've obtained the sample or the test scores from 40 people from Professor Cooper's class, and we're interested in knowing the test scores for all introductory stat students, that group of 40 is now our sample. So keep in mind that populations don't always necessarily have to be big. Populations are how we define them. However, most of the time, a lot of the times in psychology or in research, we do have large populations that we might not necessarily know the exact number for. So when you're obtaining a portion of the population, like in the example here, we're interested in test scores for all stat students. We obtained 40 students from Professor Cooper's class. Obviously, the 40 of you are a portion of the larger population of all students in Introduction to Stats. So when we have just that portion, sorry, the air quality is just messing me up. I don't have COVID. But when we just have a portion of it, a sample of it, well, then we have a sample of it. But when we just say we're only interested in the 40 people in the class, and that's the test scores I care about, we've defined our population as just these 40. Now that can be changed to, oh, you know, the population, I'm interested in the American public. I don't have access to all of the American public. And if I say I obtained a sample of 10,000 people, that's a big sample, but that's still not the population. That's not including the entire population of the United States. Or I said the American public. I mean, the United States of America, that's just there's South America, there's Central America, there's North America. So when you say American public, it's kind of like, well, you know, the United States isn't the only Americans, but anyway. So why is it that we're taking samples? Why does it matter? Well, depending on how large that population is, like the American public, it could be impossible to obtain information from every single person. Let's say there's 2 million people in our population of, I don't know, maybe introductory stat students in California. Let's say there's 2 million, just make it easy. Well, if we send out a survey or send out whatever it is that we're asking these students for, or if we're like trying to obtain test scores, and there's 2 million in the population, and we get 1,999,999, we're missing one person, that is still a sample. Even though we have most of the population, we're only missing one person who didn't get the email or whatever. That is still considered a sample because it is a portion of the population. It is not all of it. But when we take these samples, regardless of how large or small they are, if it's a sample, we don't have access to the whole population. So this sample is meant to serve as a way to generalize information. Maybe we get you know, in our sample of 40 students to generalize to the introductory to stat students, I'm going to take the exam scores for the first exam, which is going to cover everything we've covered up to this point, including this week of lecture, so characteristics of the sample mean. Well, if I take if I give you guys your exams, and then I take the measurement or take the means and standard deviation from your test scores, and I want to generalize that to the population. Let's say you guys get an average of a 70%. I'm like, okay, so if I generalize this to the population, that's saying that after the first exam covering these topics, because obviously different professors might have their exams at different times, but after giving an exam on these topics, 70% is the average. So I'm going to use that to generalize to all stat students. When they take the exam on these topics, they will get 70%. So since populations are so large, again, you got to define it. So is it at Fresno State? There's still a lot of introduction to stat students at state. Is it in Fresno? Is it in California? Is it in the United States? Is it the world? You just have to think, well, okay, if I'm just generalizing this to this large population I'm not entirely sure the exact number of, I have to use samples. I don't really have another choice. So it's one thing to just take a sample, that 70% of the exam, and think, oh, well, that's the mean of the population. But we have to think, how close is this 70% to the actual population? If we were to actually get the exam scores from all introduction to stat students and find the means and standard deviation, we'd know for sure the population mean and the population standard deviation. But when we take this 70% from the 40 students in our class, how close are we to knowing, okay, so we're generalizing this to be the population of 70%, but we don't really know that for sure. We don't, because we don't have every single introduction to stat students exam scores. So we have to think what's the probability that this sample of our 40 students with our 70% average is going to be larger than or smaller than or exactly equal to the value of the population mean? How do we know that? There's a solution to that, the sampling distribution. So we have a population distribution, which is all exam scores for every single person in Introduction to Stats, and it follows probably the bell curve. It'll probably be a normal distribution where, we've seen it with when we went over z-scores, just that typical typical bell curve that we're used to seeing. The sample distribution, which is just taking a look at one sample. So our 40 students, we can put that on a bell curve as well. It might be a relatively normal distribution, just depending on the sample. And then the sampling distribution is not the entire population. It's not just looking at the population straight up. It's not looking at one sample of 40. It's looking at every single combination of samples of 40 within the Introduction to Stats students population. So the sampling distribution allows us to kind of think of, okay, how likely is it that our sample of 40 students with their 70% average, how close to the true population mean is that? So we have the sampling distribution, which is the distribution of every single combination of 40 students. It's a lot of samples, a whole lot of samples that we're dealing with here. So with that, no, Amelia, go, I am working. I love you, but no. So with the sampling distribution, we're not just taking one of the little things at Costco. We're not taking, they're in your room. Oh, fuck. Okay. So we have all of the samples. So it's not just taking this one sample from this, cowboy hat gentleman and saying, ooh, this parfait's delicious. It's taking his his groups of samples. It's taking all the groups of samples from the guy on the night shift. Well, they don't really serve samples during the night shift at Costco, but it's taking all of the possible samples, not just the ones on the plate, but the ones that are in the entire store or the entire population. So there are different ways to gather participants for samples. I talked about how, oh, our 40 stat students, in our class, and that's our sample of 40 that represents the entire population of introduction to stat students. Well, there are different ways to get different samples. So there are two different ways. One is sampling without replacement. So when you have your population of introduction to stat students, you select a participant, you select one of the students, and that person is not put back into the pool to choose from. So imagine if you are going to have, if you're playing like PE, or if you're playing PE, my God, if you're doing like a game of pickup basketball or any sort of game where you're required to, pick your teams. And it's like, okay, we want the really tall guy, he's really good. We want the, the medium height, but really good basketball player over here for our team. Oh, the other team, oh, I want that guy. Sampling without replacement is essentially picking teams for sports, or picking players for your sports, where it's not like once you pick the super tall guy, you're going to put him back in. It's like, okay, I pick him. We'll just have him for 2 seconds, and then I'm going to put him back in the, in the pool for you guys to pick. That's why it's so important that you want to pick first in that kind of situation, because it's sampling without replacement. Once you pick the really good guy, the really tall, good basketball player, you don't have to worry about him going back into the draft, for lack of a better term, but you don't have to worry about him being on the other team. You picked him. He's in your sample. That's sampling without replacement. Sampling with replacement would be, you pick the guy, cool, you're on our team. Okay, now go back there. We're gonna keep picking. Like, okay. So sampling without replacement is like picking teams in sports, or picking teams for like PE or whatever. Sampling with replacement is like, doesn't make any sense when you're picking teams for sports. So once you pick someone for sampling with replacement, you pick them, and then you put them back in the available pool, and you could pick them again, and that would be considered a sample. I'll get more into that later. So with behavioral sciences, psychology is included in this. We typically use sampling without replacement, so the traditional sports team picking method, where we keep them and we don't throw them back into the available people to choose from, because the populations that we typically deal with in behavioral psychology, or just, well, psychology, they're so large. We're interested in the behaviors and the tendencies of people, and that's a pretty damn big population. So since our populations are usually large, be it like, oh, college students, men, women, just people in general, maybe elderly people over the age of 65, maybe children under the age of 17 or 18, whatever. Our populations are typically large. So to have us use sampling without replacement, it typically is not an issue for us, because we're typically probably not going to pick the same person twice, considering the probability of that is so low, considering how large our populations in question are. So we talked about sampling with and without replacement. So we have sample design, where this refers to how we pick people. So all sample designs address two questions. We have, does the order of selecting participants matter? And do we replace each selection after the next draw, or before the next draw? So with theoretical sampling, the order of selecting participants does matter, and we do replace selection before each draw. So this is a sampling without replacement example. And this is theoretical, keep in mind. So this doesn't really happen in real life, but when we talk about statistical theory, when we talk about, I'm going to get into it later in terms of characteristics of the sample mean, it uses theoretical sampling because, again, we got to use the theory. We're going to enter the statistical la-la land right now. This is like, ooh, perfect world, but it's never perfect. Anyway, so if we have a population size of 3, capital N equals 3, population size is 3, and we're taking sample sizes of 2. To obtain the total number of possible samples, we take the population size to the power of the sample size. So again, our population size was 3, and our sample size was 2. So 3 squared is 9 total possible samples when we have a population of 3 and taking a sample size of 2. So just to kind of show you how the order does matter, and they are being replaced back into the theoretical hat to pick the name from. Here's our sample, or well, our population. With n equals 3, capital N, our population size is 3. So our population is A, B, and C, and we're taking sample sizes of 2. So you see over here in this table, you see A, B, and C, but each of them, their sample sizes are 2. So we have AA, AB, AC, BA, BB, BC, CA, CB, CC. Those are all considered different samples because the order matters. So AC is a different sample than CA. Even though the same exact letters are there, it's still considered a different sample because with theoretical sampling, again, the order does matter. So AC is a completely separate sample than CA. And in selecting our participants to be in our samples, there is replacement. And that's most evident through these doubles, AA, BB, and CC. Obviously, they have been replaced in the pool of, I'm going to choose a sample because A has been selected twice. They have been replaced, and then with the next draw, they get A again. So A. Okay. So the order matters, and there is replacement. Again, just really quickly, I said that, oh, you know, to find the total number of samples when you're dealing with theoretical sampling design with a population size of 3 with sample sizes of 2, 3 squared is 9. That's how you find the total number of samples. 1, 2, 3, 4, 5, 6, 7, 8, 9. You will see 9 total possible samples here. So that's what that is referring to. Okay, now the other sampling design is experimental sampling design, where again, addressing those 2 questions, does the order of participants matter? No. And do we replace after each selection before the next draw? No, we don't. So this is typically what we're more used to. This is something that kind of, you know, makes more sense. So the order of participants matters. So this is kind of like thinking about picking teams for a basketball game. You know, you have 10 people, 10 people, you choose 2 captains, and then they have to pick the remaining 8 people to make their teams of 5. Anyway, so the order of participants matters. If you pick, you know, super tall guy, regular size Rudy, I've been watching a lot of Bob's Burgers, but if you pick super tall guy, regular size Rudy, LeBron James, and I don't know, Chris Bosh, that's the same team as if you picked regular size Rudy first, then LeBron James, then the super tall guy that's good at basketball, and then Chris Bosh. It's still the same team. Even if the order is a little different, you still have the same team of, I don't know, they're not on the same team. Although, did LeBron James and Chris Bosh used to be on the same team? I know they both played on the Heat. Anyway, so I digress. And do we replace each selection before the next draw? No. Once I drafted LeBron James, he's mine. Like, I don't want to put him back in there. He's on my team. I called him. I got him. So experimental sampling, you can kind of think of as, you know, picking teams in sports, where if you pick LeBron James first and then Chris Bosh and then the tall guy that's good at basketball who just apparently doesn't have a name, and then regular size Rudy, that's still the same team as if you pick Chris Bosh first and then tall guy good at basketball and LeBron James and then regular size Rudy. I always have regular size Rudy first because obviously he's regular size Rudy, although bless him, he has asthma. Anyway, so if we have a population size of 3, so let's use that same example that we did before. We have a population size of 3, and we're taking sample sizes of 2. So just like how we did previously with theoretical sampling, when we did this equation and we got 9 total possible samples because the order of participants matters and we do replace after each draw, let's see the difference of how many total samples there are when we use experimental sampling. So of course there's a different equation because, of course. So with this, we have, I like to just make it exciting. Well, I mean, it's just, you know, theoretical, or it's mathematical notations here, but I just like to go population size divided by sample size. And then you take population size minus sample size. because the exclamation points, I'm just trying to be dramatic here. But anyway, what these mean, what these exclamation points mean is that this top number here, the 3, so the population size is 3 times 2 times 1. You're just breaking it down to 3, 2, 1, all the numbers within. And you just make that, you multiply that, and this 3 is 6 because you're taking 3 times 2 times 1. And then essentially whatever number you have, you're just counting down. So if that number were to be 20, it'd be 20 times 19 times 18 times 17 times 16, all the way down the line. But I wanted to use smaller numbers just to make it, so we didn't have to worry about, just to get the very gist of it down. So we take that 3 times 2 times 1, divided by 2, which is just 2 times 1. So you see that here. And then in the parentheses, we have to do those first. So the 3 minus 2, that's equal to 1. So 1 times 1. I'm not going to bother doing that. But anyway, so we take the 2 times 1 times, which was this, the 2, and then times 1 is what we did for the parentheses. So 2 times 1 is 2. So anyway, the total number of possible samples for experimental sampling when our population size is 3 and our sample size is 2 is going to be 3. 3 total possible samples. And again, just to visualize that, here it is. So since the order doesn't matter, so AB is a sample. If BA is not a separate sample, again, you have LeBron James and Chris Bosh on your team. Having Chris Bosh and then LeBron James on your team, it's not different. It's the exact same. So the order doesn't matter. And there's no replacement. So we're not seeing LeBron James. You can't have him twice on your team. I mean, as much as we'd like to. But you can't have LeBron James, or Chris Bosh. You just have them once. That's it. So that's the no replacement. So there's no sampling with replacement here in experimental sampling. And it makes sense. We have this experimental sampling. We only have 3 possible. So boom. All right. So just to kind of get you more familiar with working with that equation, I mentioned how longer numbers is going to be more drawn out. But just so you guys are comfortable, I use those smaller numbers just to get you the gist, and because it's easier to show the difference between experimental and theoretical sampling with smaller numbers. But just to get you guys comfortable, you guys will be doing these sorts of things for your exams. So just to get you more familiar with that. Let's say we want to use the experimental sampling equation. So we're using experimental sampling design. And we want to see how many total samples are possible if we have a population of 10 and we're taking samples of 3. Okay, so here's the equation. We're gonna just plug it in. So again, 10, that population size is on the top. Then we have sample size, so the 3, and the population size minus sample size, that 10 minus 3. So we have 10 divided by 3 times 7, because 10 minus 3. So of course we do the 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. You don't really have to include the times 1 because it's like, okay, but anywho. Divide it by the 3 times 2 times 1. That's that first part here. And then you'll see here it starts to go to 7 times 6 times 5 times 4 times 3 times 2 times 1. Well, that's referring to, again, we did the parentheses first, remember PEMDAS, but we did 10 minus 3, so that's 7. And now we do the 3 times 2 times 1, and then times 7 times 6 times 5 times 4 times 3 times 2 times 1. So that goes into 3,628,800 divided by 30,240. You do that and you get 120. So when you have a population size of 10 and you're taking sample sizes of 3, there are 120 possible samples that you can get. Okay, so the sample mean, kind of coming back to the sample mean, we know how to do sampling design, theoretical, how many samples are possible with theoretical sampling and how many possible samples there are with experimental sampling. But when we look at the sample mean, again, how do we know our sample of 40 stat students can apply to the whole introduction to stat students. How close is our 40 is our sample size of 40 with our average test or our average exam score of 70? How close is that to the true population mean? Is it too high? Is it higher? Is it lower? Is it right on the dot? I don't know. So in that, so the sample mean refers to the population mean, relates to it, excuse me, in three ways. Now my nose is itchy. The first is that it is an unbiased estimator. It follows the central limit theorem, and it has minimum variance. Now, obviously, I'm going to go into more detail with these because I know just telling you these things, it's like, oh, okay, I get it now. I'll go into more instruction on that. But of course, since we're getting more into sample means and more theoretical, like statistical, ooh, la la land, where this doesn't never really happen, but we have to just kind of make the best of it. We're using theoretical sampling design in all the ways that that the sample mean applies to the population mean. So first, let's talk about the sample mean as an unbiased estimator, excuse me. So the sample mean is an unbiased estimator when we obtain random, okay, so we have our sample size of 40, and however many, I don't know the population size of, you know, how many introduction to stat students there are. But again, to take the total number of samples, total number of possible samples, let's say it's like 2 million, again, just in California. So we have 2 million, and since our sample size is 40, it's 2 million to the 40th power. That's a boatload of samples. But if we were to take all of those total possible samples, and with each individual combination of 40 people, so again, it's just a free-for-all. If we were to find the average exam score for each of those 2 million to the 40th power, each of those numbers of samples, we'd find an average. So our class, our sample in particular would be 70%, maybe a different combination of 40 from this total 200 or 2 million population. Maybe a different combination would be, I don't know, 68%, maybe you get a 75, I don't know. You'd have all these different types of means. So the unbiased estimator is saying that taking a randomly selected sample of all those, like the tons, the multiple million billion combination of 2 million to the 40th power, that's a boatload of samples. If we were to select any one of those, on average, it would equal the population mean. Now, I usually have an example to demonstrate this in smaller quantities, but essentially, if we were to apply numbers to that theoretical example we had earlier with a population of 3 and a sample size of 2, if we were to apply numbers to all those, like, oh, A equals 4, B equals 5, C equals 6, and we found the averages of each of the 9 total possible samples, you know, oh, A was 4, I think I said, AA, so 4 plus 4 is 8 divided by 2. The average of AA is 4. The average of AB would be 4 plus 5, so 9 divided by 2 would be 3.5. So wait, 4.5, my bad. Anyway, so to if we were to find all the averages of all the theoretical possible samples, once we average those averages, it will equal the population mean. I know. It's a mess, but essentially, to say that the sample mean is an unbiased estimator is saying that if you select the sample mean, it's going to equal the population mean on average, meaning that when we take all of the averages of the possible sample combinations, again, that 2 million to the 40th power, we find the average of all of those groups. On average, it'll equal, when you average all of those together, it does equal the population mean. So on average, when we select it, it does equal that. Whew. The central limit theorem is saying, so again, first, the sample mean is an unbiased estimator. Second is that the sample mean follows the central limit theorem. So although all scores of a population might not be normally distributed, again, that bell curve, the normal distribution curve that we've seen with like z-scores, let's say, Even if the scores for the population aren't normally distributed, the sampling distribution, again, the combination of all possible samples of 40 in our population of 2 million, let's say, again, I'm just winging it. I don't know the exact population of introduction to stats students in California, but I'm just using that number so to make it easier for us to kind of think about it. Central limit saying that even if the distribution of exam scores for the 2 million population of introduction to stats students test scores, even if that distribution is not normally distributed, the total combination of all of the students in samples of 40, that distribution, the sampling distribution, will be normally distributed. So that is the central limit theorem. Even if the population isn't normally distributed, the sampling distribution will be. And again, that sampling distribution is all possible combinations of our sample size of 40 in the context of a population of 2 million. Again, this is my example. Okay, so since it is normally distributed, since the sampling means, since the sampling distribution is normally distributed, we know that 95% of the possible sample means are within 2 standard deviations of the population mean. Since it's normally distributed, it does follow the empirical rule. So 2 standard deviations above and below the sample mean, that's where 95% of our, 2 standard deviations above and below the population mean is where 95% of all our combinations of sample sizes of 40 in a population of 2 million, 95% of them lie between 2 standard deviations above and below that mean. Minimum variance. So we do have to have a positive variance, or keep in mind, this is also this is a measure, this is a measure of variability. So when we have sampling distributions, not everyone's gonna have the exact same score. I'm sure that if we take a combination of every single possible, if we take the means of every single possible combination of 40 in a population of 2 million, we're not gonna get the same exact score all across the board. That's just not gonna happen. So we have a minimum variance. We have at least, our variability is not 0, meaning that not everyone scored the same. So minimum variance is essentially saying the scores that you get are going to be different. Essentially, that's what it boils down to. Now, the sampling distribution has a slightly different formula when it comes to calculating the variance of the sampling distribution, So here it is. Again, sigma squared, that is referring to variance because that's square. If it didn't have square, that would be the standard deviation or standard error. But this sigma squared m refers to the variance of the sampling distribution. That's what that little m is representing. Equals the sum of mean minus the population mean squared. So this is the same stuff that we see in the variance formula, except for population or sample variance, we're not seeing as many of these like, mean of the distribution. We're not seeing that because it's just a straight up population or sample mean. But again, the sampling distribution gets a little more complicated. So what this whole thing translates to, just to put it in perspective, is the variance of the sampling distribution of the sample means. So again, this equals the sum of each sample mean. So the sum of each sample mean minus the mean of the sampling distribution squared. So that is representative of that part. These words here represent this here. Oh God, I'm moving shit around. Okay. Okay. Represent that divided by the total number of possible samples that can be selected. So again, it's using theoretical sampling design because all of these things that have all of the different ways that the sample mean relates to the population mean, like I mentioned before I got into estimated, unbiased estimator, central limit theorem, and minimum variance, I stated that they would all follow the theoretical sampling. Well, that's what we have here. It's following the theoretical sampling. That's how you calculate variance of a sampling distribution through theoretical sampling methods. Okay. Okay. So we know the variance of the sample distribution. Standard deviation, it's not quite called standard deviation when it refers to the sampling distribution. Instead, it is referred to the standard error of the mean, or you can just call it standard error. So once we take this formula and calculate the variance of the sampling distribution, once we square root that, we find the standard error of the sampling distribution. So this is just telling us how far all the possible sample means deviate from the value of the population mean. Okay. So that's all I'm going to cover in this lecture. I told you that it's going to be really heavy on like theoretical, statistical stuff. So if you need to take a break, if you need to, you know, I don't know, smoke a cigarette, or, well, you know, I'm not going to encourage you to smoke a cigarette, but anyway, you know, if you need to like take a minute, I don't know, play a video game to get this out of your head for a second, I understand completely. But just keep in mind that the stuff I'm talking about today and just this week definitely refers to, it has a lot to do with how we're able to infer information from our samples to a population. So when we take our sample of, oh, 40 stats students, and this is our mean of 70%, yeah, that's gonna generalize the that's what we're generalizing to the population. When I'm saying stuff like samples generalizing to the population, this is the man behind the curtain. This is the reason why we're able to say this sample generalizes to the population. So just to give you guys a point as to why we're learning this, it seems like, oh God, like what? I know, but this is kind of the recipe or the method behind the madness of us being able to say, oh, we use samples to generalize to a population. This week is how we do that. So anyway, if you have questions, I don't doubt that you would, but if you do have questions, don't hesitate to email me or inbox me in Canvas or come to my office hours. I'm happy to answer any questions you have. If you're crying because of this lecture, I'm happy to, you know, pat you on the back. Well, metaphorically pat you on the back and say it's going to be okay. I know this is a shitty week, but don't worry. But anywho, I hope you guys are having a good time. Maybe not in relation to this lecture, but anyway, again, if you have questions, just let me know. And that's all I got for you today. So like and subscribe.